Welcome back to Design a Computer from Scratch. This is part 8 and should conclude the goals that we set in the initial part of having a computer that has a minimal instruction set but enough to do some I/O crunching and moving data around. This particular section is on the arithmetic logic unit and conditional branch design. Just as a refresher, the goal of the ALU, or the function of the ALU in branch control, is only used for our AND register immediate instruction. In the ALU, it takes two 8-bit values in. One is the immediate value in the instruction from bit 7 down to 0, and the other one is the register that is selected from the register file by D11 down to D8. So basically, you can look at the instruction and know which register it's coming from and what the immediate value to AND it with is. The result of the ALU is an 8-bit result that's stored back into that register that was addressed by 11 down to 8, plus a 0-bit that said that the result of that ANDing produced the 0 result. The opcode itself determines the ALU operation. The only one we've implemented is the ARI, the AND register immediate. But you'll see as you go through it how easy it would be to do an OR register immediate or an add register plus immediate. Let's start out by creating a new VHDL file. We're going to call the file alu.vhd, but the entity will name different. I said I don't like to normally do that. I did it this time. I could do it, not do it, but I called the entity ALU_unit. Let's look at what is on the entity that pins into the ALU, the clock, that 50 megahertz clock. The ALU will run at 50 megahertz. It has two sets of 8-bit inputs, ALU input A and ALU input B. Since we're only doing an AND instruction, it doesn't really matter which 8-bit values you hook up to which, but if we were doing an add, it wouldn't matter either. But if you were doing a subtract, it would matter. You'd have to do the subtract in the correct direction. Do you subtract the immediate from the register, or do you subtract the register from the immediate? Probably want to subtract the register minus the immediate, so you'd have to make sure you get these two on the right place, and the math would have to be done right. So the opcode also goes in here. If we had more opcodes, they would be added here in the list. Maybe an op_ORI, ORI, or ADD, or some other opcode, ADI, maybe. Anyway, the other input that goes in is a strobe that strobes the Z bit and latches it up at the proper time from the state timing. The two outputs are the Z bit, that single bit that's latched up that tells whether that operation resulted in a value that was 0, and the ALU out, those 8 bits out of the ALU, which is the result of taking these two and applying that operation. ALU code's really not very complicated. The ALU out, 8 bits of data. This particular operation here does a bitwise AND. We're used to maybe saying AND in terms of 1 and 0, but this is ANDing the 8 bits of the AN and the 8 bits of the BN and producing that output. And it's only doing that when the instruction is the ARI, the AND register with the immediate value. If there was a OR, let's say, it would be exactly the same, except instead of saying AND, it would say OR, and instead of saying OP ARI, it would say maybe OP ORI, or if there was an add, it would be something very similar. It would just be lines added on to the output here, essentially as a multiplexer. We really could have got by for just the ARI without having everything from the when on to right before the semicolon, just stopped it there with the semicolon, but having the flexibility or sort of building it in as if we're going to add instructions is a useful thing to do. So the next line is a wire. The last one was an out of the entity. The next one's a wire that's inside of the entity, and it's a flag inside that looks and sees, is every single bit in that ALU out, is it equal to 0? If they're all equal to 0, then it's a 0 value. And we want to latch that up, so we do the classic sort of process here for the ALU unit. This really probably could be called something better like latch Z bit or something, but it's really doesn't matter what we call it here. But it probably, like I said, probably properly should be latch 0 bit, because that's really what we're doing here. And on the rising edge of the clock, it looks and sees, is the result 0? If so, latch it up. And then because it's an O, it sends it out. The signals and test pins here, we'll add those for signal taps so we can see what's going on with the ALU, and then we'll add those signals and compile. Having those signals, the ALU in and out and ins and out, and the 0 value will give us a good idea of what's going on inside of the ALU. The entity that gets added to the CPU underscore 001 VHDL file is that ALU unit. Remember, you reformat stuff over here. You add the colon, you add a name, you add work dot, add the map. Don't put the line after it, and that's pretty much the format you need. Put in the maps to symbol, the equals greater than, and then the thing you want to hook up to inside of the top. So we hook up to the 50 megahertz clock. We hook up to the register file out, so that's the register that's selected out of the register file. It's already done inside of the register file, but it's those 8 bits from the register file. The B that comes in is the immediate data straight out of the ROM. Doesn't need to go through anything else. We're throwing in that ARI opcode, and we want to latch up that Z bit when the ARI is set and the code is 1, 0 or state 2. Same thing we're doing for everything else. That'll preserve it into the next instruction. It'll only get set when it's in state 2 and there's an ARI. We would expand this out for other opcodes if we wanted to do other opcodes, but that basically would cover it. It's probably better to have the gray code stuff all done in the CPU top section, not inside of the file. And we could have sent in the gray codes and done that decode down in here, but if you want to dink around with the timing, it's a lot easier if it's all in that one file and you don't have to go into other places to find it. The output Z bit goes to a wire, and I think I mentioned earlier I should have named this WALU data out. Hopefully NAND isn't disappointed in me. And of course we want to comment out the current patch we had, which just took the register file out and read it back in. Now we've actually got an ALU. So let's do some test code to see how that worked. And for this test code, we'll play with 2 registers. It would be kind of nice to check a couple more registers. We'll load register 55 with, or register 0 with 55, and load register 1 with the value of AA. And then we'll AND each of those with 1. If we AND 55 with 1, we should get 1. If we AND AA with 1, we should get 0. So that will do all of that, and this is the list file that it created, pretty much what you would expect. And we do see that it's working, so it's running through the instructions. I think we haven't run this far before, but it's program counter 0, 1, 2, 3, 4, and then back to 0, which is the 5 lines of code that we had. The program counter is only getting loaded when it does the jump out here. This E1000 is a jump. Back to 0. We see the op ARI, there's 2 of those in a row, so that never drops. It just stayed high through 2 different instruction cycles. We see that the Z-bit latch signal comes here, and here it'll latch up not Z, here it'll latch up Z. So pretty much what we would expect it if you AND a 1 and you AND it with 55, it should be not 0, so that said not 0. And if you latch at, or if you AND an AA with an 01, it should be equal to 0, so the Z flag is set. We have everything here now that we have the Z bit working. We have everything we need to be able to implement the actual branching that we want to do from setting that Z flag. There's nothing else that the Z bit does. It only controls branching. You can't read it from the processor. It's not a register. It could be mapped into a register, but why? It's really no point. Anything you would do with it would be a logical operation that would destroy it after you did it, and you can test if it's set or not set, and you would test it by a branch instruction. So let's see, what do we have to add for branch, and what do we got to do to test it? Let's start with figuring out what we have to add. We already have a load PC when the gray code is 1 if it's a jump. All we have to do is add these two lines, and this one said same spots for gray code 1, 0, state 2, the final state. If the opcode is branch on equal to 0 and the ALU bit is set, then we want to do a branch. If the opcode is branch on not 0 and the ALU is not set, we want to do the branch. You might have to look at this for a little while to get your head around it if it's not something you played with before, but that's basically the way you would do branching in any CPU. They might have branch on overflow, branch on a lot of other stuff, and we could throw that in if we had a add instruction, but we don't have any of that. Really, the only thing the ALU can do is produce a 0 result or a non-zero result. It might be interesting to throw in an exclusive OR instruction to be able to test if it's a particular value. That would have some value to it. If you wanted to know if a 55 was in it, if you XORed it with 55, the result should be 0, and you could XOR it with 55 again to restore it if it was. So could be a few lines of code there to do actually a compare, but we don't actually have a compare. I think it would be probably better to implement the XOR function than to have a compare. The other thing here is the program counter. I think we may have already hooked this up, but that ROM data is the PC load value. So I think we must have, because the jump worked. That's what gets loaded if the load PC signal is present, which comes out of here. So the other thing to remember too is that the branches are two absolute addresses. The address literally comes out of here, and there's no calculation that's done in this path for branching. That's because we don't have separate pages. There's no page 0 or 0 page. There's only one space of the 12 bits of address for the program. Let's take some test code and see what it does. We'll start with only using register 0 for this code. Let's set it to 55 and then AND it with that 1 again. It should be equal to not 0, so it should skip this line. So that's line 0, 1, 2, 3. It should skip instruction 3. And we'll do the flip here and the flip here, and it should also skip this line. So what do we predict? We predict that we're going to skip lines 3 and 7, and it would take both branches. Here's what that assembles to the listing file. This will test the branch not 0 and the branch equals 0 for branches that are taken. It will not test them for branches that are not taken. So what do we look at? We see 0, 1, 2, skip 3, 4, 5, 6, skip 7. That's exactly what we would expect from branches that are taken. We see a load PC for the first branch, we see a load PC for the second branch, and we see a load PC signal for the jump here. We say increment PC all the way through here, but we again said about a dozen times by now that load takes priority over increment, and it's just easier to not have to say not increment. We see the instructions look clean. I'm pretty convinced that our instruction path is working. Convinced our PC runs up at least from 0 to 8, so at least 4 bits are working for the most part, and probably a lot more. It's really no good reason if something's done in a single line of VHDL code, PC equals PC plus 1, there's no good reason that a higher bit wouldn't work if a lower bit works. We also see when we're doing the AND register immediate, we see that latch of the Z bit happen with every time, and we see new Z bit set. So we see it set through here, we see it cleared through here, we see it set through here, and we also notice that the Z bit says sticky. It sticks around even through the jump back to 0 here. So you could do a AND and then a bunch of other stuff and then come back and look at the result with a comparison later on. Although typically you're reading a UART status register, you're looking at that status bit and you're looping or skipping. If you want to see is there any data, wait for data, then you would jump back to waiting till there's data present. If you want to see if there's data and do something with it, you would jump around it rather than looping back if there wasn't data. So this produces all of that function. This is really everything we were trying to do in the very beginning. What we haven't checked is branches. Well, actually we did. No, we haven't checked branches not taken. We would expect if we play with the code to be able to see the 3 and the 7 addresses. So let's do that. If we take the same code and all we do is make the decision to branch on equal to 0 instead of not 0. Remember, this was not 0 before, and this was equal 0. Now we're changing it to not 0. So we flip that original code, and so we should see it go through all 0 through 8 steps here. And by gosh, we see that 0, 1, 2, 3, 4, 5, 6, 7, 8. So it's running through all of them. It's not taking the branch. We don't see any load PCs except on these two ends where the jump happens, and the address counter is going just like it should. So it looks like we've accomplished the result we wanted. We can see the ALU out is correct. It's pretty much doing everything we would exactly expect it to do. Z-bit still staying set like we would expect as well. So what did we do in this section? Well, we accomplished all of the original design objectives. And I could end the video series here. Hey, I might. Depends upon how I feel after doing all this. But I think I'll probably do some more. But we accomplished all the design objectives. We basically have something that could execute our initial easy app, which is read a button and write a light. But hey, I never did that. I'm going to follow the old college professor's line of that exercise is left for the student. Feel free to write that code. We know it works because we have talked to a peripheral register, inverted it, and read the value back. So we know it's able to do all of that. We have a very minimal set of instructions. We have the 0 flag working in this particular one. We made sure ARR and register immediate worked. We made sure the 2 branches worked. But as far as what we've done, we've only implemented 4 of the registers, or tested 4 of the registers. We implemented a register 0, 1, 2, 3, and then we implemented an R8, which is equal to 0, and R9, which is equal to 1, and an RF. But we haven't tested some pieces of that. It would be nice to test those as well. That's where the signal tap logic analyzer can be really helpful. You can write a bunch of test cases to play with stuff, and you're not relying on anything other than what's inside of the tool. You can look in the trace just like we did and see, oh yeah, I loaded that register and it got loaded, and I wrote it out to an I/O port, and I see all the strobes. You can see everything from inside the logic test analyzer, signal tap logic analyzer. The only cost of it is just the time of recompiling, because every time you change a trigger, change a condition, change anything, you have to recompile it. But it's definitely good. Well, where does that leave us, and where can we go from here if we want to go further into this? Before we answer that question, let's take a look at what the resources used inside of the FPGA are, because that's always the classic question. How big was that? You go out for a job interview for an FPGA job. Well, how big was that design you did back 20 years ago? I don't know, 100,000 gates. No, I don't think so. This is really tiny, really, really tiny. It only uses 144 logic cells. One thing I did do to make sure that the space is minimal is reduce the ROM size to 512 of 16-bit words. There's no point in going any smaller because it has to use 2 M9K cells. You can certainly go bigger. This is a pretty large program to begin with. I haven't written anything this big, and I've done a few complicated applications with this that didn't require anywhere near 512. The other pieces we see here in terms of allocation, utilization, ALU only had that Z-bit, so there's only 1 register, but it only used 45 ALUs, or logic cells inside of the ALU. It'll use quite a few more as we start adding other operations. If you do an add, the adder will add in there. If you do XOR, it'll be very similar to the AND. If you do an OR, it'll be very similar to the AND, but this thing will scale up. Grade code counter only used 2 registers, 2 logic cells for those 2 registers. It's a 2-bit counter, pretty simple, but very powerful. Program counter is kind of where you might shake your head and go, well, what's going on there? Well, we had a 12-bit program counter. Well, it knew that the program size, and this is where Quartus is just amazing, it knew the program size was 512 words, so it knew it only needed 9 bits to access that ROM, and that nothing was going to use the upper 3 bits. Therefore, it optimized them away in the design. You could probably find some way to preserve them and look at them, but unnecessary here. we do have the space to go bigger, and it would use more if you use more resources. That register file is pretty small so far. The cost of the register file is really only in the registers so far, most of it. And that's the 4 registers with 8 bits. The constant values sort of show up over here in the logic cells. And if you add more constants, this number gets bigger. If we add more registers, this would get bigger. If we had all 16 times 8, we would have 16 times 8 registers used. But we're using a fairly small amount in this design so far. Mentioned the ROM file is 8K bytes worth of ROM, or excuse me, 8K bits. That's 512 words, where a word is 16 bits. Uses 2 blocks. If we wanted to make the instruction set a little bit bigger, instead of 16 bits, make it 18 bits, well, we'd break the assembler. We'd have to fix that, which is a little bit of work. But the other thing we could do that, because these memory blocks are 9K blocks, so we have an extra bit left over on each one. So if you wanted a bigger register file, you could throw a bit or 2 there. If you wanted, instead of having 16 instructions, you want to have 32 or 64 instructions, that could be done there as well. And it would come at 0 cost. Now, probably some cost for the combinatorial logic and things that hook up to it, but no cost in terms of memory. And often memory is the thing you're trying to preserve for other functions on what you're designing. Usually the logic has plenty of room in these. Our little peripheral test register, well, we're counting it in our 144 and our 52, but really we could subtract it if we wanted to say, well, how much does the CPU use without it? I think that's, 100 and, I don't know, I can't do math that's that high. It's less than 144 and 52. So, nice small device. Remember, there's 15,000 logic cells inside of this part, and we're only using 144. So a very small percentage of them. You could throw quite a few of these in there, and you'd quickly run out of RAM. Maybe if you put 26 of these inside of there, you'd be up to the 52, or if you put 23, you'd be up to the, or 28, you'd be up to the 56. Excuse my math. But that would be a lot of little tiny processors. Probably not something you would need to do, but hey, you can go quite a bit bigger. But again, your limitation's probably never going to be logic cells with something like this, even if you make the instruction set a lot more complicated. It's always going to be the RAM, or nearly always going to be the RAM. Now, there could be a trick done here. If your program was small enough, you could replace that ROM file with constants, and it would get implemented in logic. Have to spend some time thinking about that, and perhaps looking at timing to make sure that it didn't get away. But that is a way to replace the RAM and free up that RAM. It seems like a waste for a 5-line program to use up 2 full blocks, but hey, that's what we did. What sort of features would be nice to have? Well, gosh, I made another version of this, and the other version I made, I figured out how to get branch to subroutines. Probably really more accurately put as jump to subroutine. This is not a relative branch, it's an absolute jump. But the return from subroutine would return to the next address after the calling address. And that's a very cool way to save code space if you're doing something repeatedly. In that particular instance, I was driving a card with 4 I2C expanders on it, and each of the cards or each of the I2C expanders had the same basic initialization code. So if I just wrote the code once, but it wrote to quite a few of the registers in it, I could write the code to write to the registers one time and call it from any place I needed it. That took approximately 1,000 lines of code, which was long and a little difficult to debug and very repetitive, and turned it into 256 lines, give or take. So that was a 75% drop. The question you come to when you kick around, or am I going to do a branch subroutine and return from subroutine, is do I want to be nested, or is a single depth good enough? If it's single depth, then you can just store the next address plus 1 from where you're at whenever you do the BSR, and then pull it in a similar path to what we do for the return from subroutine, the jumps or the branch subroutines. Load it, you can just load the address from there. So that would only use the 12 bits of the register. If you want to do a deeper set of nesting, you won't get the same return. I took that same application, put a deeper FIFO or LIFO on there for the stack, and it only took it down by a few percent. That big gain was in having one level of subroutines. To have 2 or 3 or 4 or 12 nested subroutines, it was really diminishing returns when I did that. And it does come at the cost of RAM if you use a standard LIFO that's implemented with memory. If you wanted to implement a LIFO without memory, you can spend some time thinking about how to make something that's a LIFO last in, first out. I did a Google search or a search on GitHub and found somebody had a piece of VHDL code up there, and I used that. It was took a little bit of fiddling with it to get it to integrate with my code, but in the end, it just really pretty much just worked. Making the stack is more complicated, but it really isn't in the end. LIFO just shoves stuff into the list as it comes in and pulls it out as it goes out. So whenever you branch off the subroutine, you shove in the return address +1, and when you return, you just pull that and jump to that next address. It's probably best to do that calculation when you're pushing it on the stack rather than returning, because otherwise if you're pulling it out and then you're adding, it takes extra time. You got plenty of time to do it when you're stuffing it away to go off to a subroutine. Might be fun to add an OR instruction in here. My front panel application did need that, so my other version of this processor does have that instruction. That's because the I2C interface has two different addresses for master or for writes and reads, and I just needed to do the write first and then OR in a bit to do the read. That was a good way to get there. I could think of other applications that would want to use it. It's more useful for what it does for data rather than for setting flags, because almost anything you OR, if you had any value and you OR any value with it, you're going to have either, if the value was 0 and you OR 0 with it, you'll get a 0-bit set, but any other time, anything that was in the register or anything you OR with it is going to be not 0. So it other than for doing a compare equal to 0, it's not super useful. There's probably better ways to do a compare equal to 0 with this architecture. You could just do an AND with FF. If the result was 0, you'll set your 0 flag. So OR and the Z flag aren't really necessary, but ORing of that bit to use it for functions is. The other thing that comes out back to the branch or jump subroutine and return from subroutine is you then have to start spending some thought about register allocation. I ended up using reg 0 through 3 or 4 for parameters that I passed down into the subroutine, and I returned back values in R7. So that was a useful way to pick a standard sort of a convention for what I did. You could do any convention you want. You could send it down in R0, return it in R0, do whatever you want, but it was convenient for my particular application. My point is you've got to spend some time thinking about where your registers, what are you using them, are they being destroyed by the function they're in. Actually, I don't think I did that. I think I used the R7 for testing ready bits on the port, and I think I passed values for writes in R2 and returned them back in R2 to be more correct. That makes more sense, because then you could do a function to do a read and then a function to do a write in order, and you don't have to move anything between the registers. But again, you have to spend some time thinking about how you want to use the registers, what gets destroyed where. If you're ANDing things with a register that'll get destroyed, which ones do you want to have for a scratch pad in a function, which are not guaranteed to be preserved. Quite a bit of thought there. The other thing we can implement is all of the first 8 registers in the register file, and hey, maybe some of the other ones that are not constants, but 8 would be more than enough for probably anything I would ever want to do. Hopefully this has been helpful. The basic series is completed here. I might do a couple other pieces. This particular branch is checked in, even though this is video 8, it's checked in under part 9. I got lost somewhere. The overall design as it currently is, it'll be growing or changing, so don't count on it matching this lesson. If you want a branch that has this lesson in, I did create a branch. I also checked in a release of this particular version with conditional branches, so it'll be the first official release in the list. And as usual, the top level entity is here. Hey, thanks a lot for watching the video. I hope it was informative, and I hope you had as much fun as I did making it. Have a great day. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindy where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.